Welcome to this talk on concentration bounds for quantum states and limitations on the QAOA from polynomial approximations. I'm Tony. This is joint work with Anurag Anshu. So the main thing that we want to do here is to prove concentration bounds. And for this, we use a technique called local approximations. And I'll begin by introducing this technique kind of at a high level. And then in the paper, we use this to prove bounds for all sorts of quantum states. Here, I want to focus on two classes. One is the output states of shallow quantum circuits, and the other is the output states of something that we call dense Hamiltonian evolution, which for now you can just think of as like a generalization of shallow circuits. And it turns out that one instance of this dense Hamiltonian evolution is the evolution that's implemented by the so-called quantum approximate optimization algorithm, which I'll also explain when we get there. So these concentration bounds also apply to the output states of this algorithm, and it turns out that we can use the concentration bounds and some additional properties to prove limitations on this algorithm as well. So first, let me just say what we actually mean by concentration bounds for quantum states. And really what we mean is concentration bounds for a particular classical probability distribution associated with a quantum state. This probability distribution is called the Hamming-Weight distribution. And you get it as follows. You take some n-qubit quantum state rho, and you measure this in the computational basis. So you get some n-bit string, and you take the Hamming weight of that string. So you count up the number of ones in that string. And this will get you some probability distribution over all of the possible Hamming weights, so all of the integers between 0 and n. And this is the Hamming weight distribution of the state rho. And then when we say we prove concentration bounds for quantum states, really what we mean is we prove concentration bounds for this Hamming weight distribution. Now we can also generalize this to concentration for other observables as long as these observables change kind of slowly enough as the Hamming weight changes. But for this talk, I'll only be concerned with the Hamming weight distribution itself. So this is what we mean by concentration bounds. Why might you want to prove one? So these originally came out of quantum statistical mechanics, where they're used, for example, to prove thermalization properties of quantum states. But more recently, and maybe more interestingly for ITCS, these also turn out to be a very useful tool in quantum complexity theory. So for example, the recent proof of the NLTS conjecture by Anshu, Breichman, and Nürke uses concentration bounds as a very central ingredient in their proof. And related to these complexity theoretic applications, as we'll see later, we can also use concentration bounds to prove limitations on quantum algorithms. So just to make this motivation a bit more concrete, let me give you kind of like the meta argument for how to prove limitations from concentration bounds. And we'll later see this on the particular example of QAOA. So suppose you have some algorithm A that is meant to solve some problem P. And you should think of P here as an optimization problem, so there's some sense of kind of how good a solution is. And what we would like to prove is that algorithm A, or more broadly, any algorithm from some class of algorithms, cannot perform very well on this problem P. And for this, we prove two things separately. First, we prove that the output distribution of A must be concentrated using our concentration bounds. And then separately from that, one can, for certain problems at least, prove that any good solution to problem P produced by algorithm A can in fact not be concentrated due to some additional property of the problem, for example, symmetry. And then we can, of course, conclude that algorithm A can't perform very well on problem P. So that's the kind of high-level idea of how to use concentration bounds to prove limitations. Okay, so now let's actually dive into the slightly more technical aspect of this, which is how to prove these concentration bounds. And as I said, this goes via something called local approximations. So we need two definitions here. One is for what are called local operators. So a k-local operator on some n-qubit space is an operator R that we can decompose into a sum of terms Ri. And each term in the sum here is allowed to act non-trivially on at most k qubits, meaning that its identity everywhere except on at most k qubits. And on these k qubits, it can be anything at once. So I'll call this the local decomposition, and of course it's not unique. And also just point out that whenever I say local here, I never mean geometrically local, right? So these k qubits that can be involved in this term here, they can be any k qubits. There's no need to arrange them on some lattice and restrict to nearest neighbor interactions. So this is kind of the most general sense of locality. Then a k epsilon local or an approximately local operator is exactly what you would expect. It's just an operator that is epsilon close to a k local operator. So the sum over Ri here may be a k local operator. Then Q would be k epsilon local if the infinity norm between these two is at most epsilon. And I'll call this the local approximation to Q. And of course, it's also not unique. So just some quick examples to give you some kind of concrete intuition here. So for example, we can take the single qubit projector onto qubit I, and then take the expectation over all of the qubits. So this means it projects onto the 0 state on the ith qubit, and it is identity everywhere else. Then this is a one local operator, right? Because it's already written in this form of a sum where each of these terms acts non-trivially only on the ith qubit. On the other hand, if we, for example, look at the projector onto the all 0 state on n qubits, this would be n local, right? Because it acts non-trivially on all of the n qubits at the same time, and there's no way to decompose it into a sum of local terms. And then we could, for example, try to construct a local approximation to this n local operator by taking this one local operator of single qubit 0 projectors and taking it to some power k. And this would give you a k local operator because you sort of multiply out the terms and you get at most k of these single qubit projectors multiplied together on different qubits. So it's k local. And this would be an approximation to the all 0 projector. We can compute the approximation error here, but it's not really important. This is just meant as a simple example of intuition. Okay, so how are these local operators related to concentration bounds? This is via this lemma here, which is already kind of implicit in this earlier work by Kurihara et al. So what does this say? It says that if we have some pure quantum state psi, and its projector is a k epsilon local operator in the sense of the previous slide, then if we look at the Hemingway distribution of this state, this distribution has the following sort of concentration-like property. The probability that it is bigger than its median plus the locality k of the approximation here decays with the approximation error epsilon. So this doesn't quite look like a concentration bound yet, because in a concentration bound, really, we want to like pick a deviation k, right? And then we want to be told what the probability of the random variable deviating by that much is bounded by. But here, this works for one particular choice of k and epsilon. So you should imagine that whenever we apply this lemma, we have a kind of family of local approximations to this state, one for each value of k. And this gets us a family of these inequalities, one for each deviation k here, and collectively these behave like a concentration bound. And they also have the usual property that if you look at bigger deviations corresponding to bigger localities in your approximation, then this epsilon here will decay, right? Because as you allow a bigger locality in your approximation, you can approximate your state more and more closely, so the epsilon will decay. I should also mention that, of course, the symmetric thing also holds, right? So if you put a less than here and median minus k here, then the same thing holds. So it is symmetric, like most concentration bounds are. So the consequence of this is that to prove that a state has concentration properties, really it suffices to find local approximations to that state, right? And then we'll just run it through this lemma and get concentration bounds. Okay, so that's kind of the high-level framework for proving concentration bounds. Now let's actually prove some concrete bounds. And the first that I want to mention here are for the output states of shallow quantum circuits. So here we prove the following. Let psi be the output state of a depth d circuit on n qubits. Then for any choice of q, which is kind of like the deviation, this k on the previous slide up to some rescaling, the projector onto this output state psi is q times 2 to the d epsilon local for an approximation error epsilon, which decays like e to the minus q squared over n. So there are a lot of parameters here, but this becomes slightly easier to look at if we actually run it through the lemma from the previous slide. to get the concentration bound. And what the concentration bound will say is, let psi be the output state of a depth D circuit on n qubits as above, then the probability that this Hamming weight distribution deviates by k from its median, where k is now any deviation that you can choose, this decays like e to the minus k squared over n, and then you have this additional sort of damping factor here, which depends on the depth of the circuit. Okay, so the k here corresponds to the q times 2 to the d here. And really, like, the main qualitative feature of this bound is that if you look at constant depth, so d is just a constant, then this damping factor down here becomes a constant as well. So we get the usual Gaussian or Chernoff-like concentration for constant depth quantum circuits. So in this sense, you can kind of think of this as a quantum generalization of the Chernoff bound, because if you picked a depth 1 circuit or even a depth 0 circuit, then you could actually prove this using the Chernoff bound, and you would get the same result up to some constants. And this sort of extends this to any constant depth circuit with the same kind of Gaussian decay. So let me say very briefly at least what the proof idea here is. So because this is a bounded depth, a depth D circuit, we can use a Lightcon argument to write the output state, this projector onto the output state rather, as the classical AND function applied to a set of commuting 2 to the d local projectors. So this 2 to the d here comes from the Lightcon argument. And once we've done this, we can now replace the AND function by the optimal degree Q polynomial approximation to the AND function. So the second step here is purely classical. There's a sort of known, and it has been known for a long time, optimal polynomial approximation to the AND function. And if you plug this polynomial approximation into the first step, replacing the AND function by that, then you get a degree Q polynomial applied to 2 to the d local projectors, which gets you a Q times 2 to the d local object. And this is how you get this Q times 2 to the d here. And then this approximation error epsilon here just follows from the approximation error of the polynomial approximation of the classical AND function. Okay, so that's all I want to say on shallow quantum circuits. Now let's move on to dense Hamiltonian evolution. And I want to introduce dense Hamiltonian evolution as a kind of natural generalization of shallow circuits. And for this, let's first write shallow circuits as Hamiltonian evolution. So if you have a depth D circuit, this means you can write it as a product of sort of single layer unitaries, D of them. And each of these single layer unitaries here, you can write as e to the I times some Hamiltonian. And because in each layer of the circuit, you can only have 2 qubit gates acting on disjoint sets of qubits, each of these individual layer Hamiltonians, if you like, is a 2 local Hamiltonian where all local terms act on disjoint sets of qubits. So we can represent this by an interaction graph, which looks like this, where now the qubits are on the vertices here, and I draw an edge between them if there is a term in, say, this H1 Hamiltonian. So this is for one of the Hamiltonians. If there is a term here that acts on both of these qubits at the same time. Okay, so because of this requirement that each layer in the circuit is a tensor product of gates acting on disjoint qubits, you get this very kind of disconnected interaction graph for each of these layer Hamiltonians. Now, a dense Hamiltonian evolution is just the same thing, except that we drop this requirement that the interaction graph here has to be this weird disconnected thing, and we instead allow any interaction graph. So it's again, a product of Hamiltonian evolutions, and now each of these Hamiltonians Hj here can be any L local instead of just 2 local commuting Hamiltonian on n qubits. So all of these Hamiltonians are, of course, also commuting. We still preserve the requirement that the Hamiltonian needs to be commuting, but we now allow interaction graphs which allow interactions between any qubits of the system. Also, just to be clear, when I say commuting Hamiltonian here, I mean that each of these Hamiltonians here is commuting in the sense that it can be written as a sum of commuting local terms. But of course, the Hamiltonians in the different layers here, they don't need to commute among themselves, right? So one example, as we'll see in a minute, of such a dense Hamiltonian evolution is this QAOA algorithm that I mentioned earlier applied on dense constraint optimization problems. Okay, and now the goal here is to prove again that the output state of these Hamiltonian evolutions, so this unitary here applied to the all zero state, can be approximated by local operators. And once we have this, we get concentration bounds as before. So I want to make the kind of high-level point that it's sort of surprising that this is even true, because in the shallow quantum circuit setting, there's a very natural intuition for why you would expect to get concentration, which is that in each layer here, you have a very tight control over which qubits get correlated with which qubits, right? In this one layer, say this qubit can get correlated with this qubit, but this qubit can't get correlated with any of the other qubits. So you can really kind of manually track correlations, and this is precisely what we did in the light cone argument. This gets you some kind of weak form of independence, and this intuitively is what gets you the concentration. But the dense Hamiltonian evolution really breaks that intuition, because a single layer of Hamiltonian evolution here can correlate any two qubits with any other two qubits. Or more generally, in the L local case, it can correlate any groups of L qubits together. So I think really the update that we should make based on this 2-hour intuition is that concentration bounds arise more from these local approximations than from some kind of independence property, as you might think in the Chernoff case or in the shallow quantum circuits case. Okay, now what is the actual concentration bound that we prove for these dense Hamiltonian evolutions? We prove that if we have such a sequence of L local commuting Hamiltonians that satisfy some additional technical condition, we call it a subset norm condition. It kind of says that the weights inside the Hamiltonian are sort of well spread among the interaction terms. Then if we run P little o of log n, so slightly super constant number of layers of this Hamiltonian evolution, then the output state of this evolution is k epsilon local for k being little o of n and epsilon decaying sub-exponentially in n. So we also have more explicit non-asymptotic bounds, so you can pick a particular p and a particular k, and you get the corresponding bound on epsilon. But I picked this asymptotic version because k being little o of n is kind of the largest possible k, the largest possible locality that you can allow that's still interesting. Because if the locality k is sublinear in n, this means as n goes to infinity, the kind of proportion that each local term takes up among the n qubits vanishes, right? So it's still like very local, but it's the least local thing that's still interesting. Okay, so this talks about local approximations. We can then again run it through the lemma from earlier, and we get the probability that the Hamming weight of such an output state here of dense Hamiltonian evolution deviates by some sublinear amount from its median, decay sub-exponentially. Okay, so the final thing I want to talk about is how to use these concentration bounds to prove limitations on this QAOA algorithm that I've referenced a bunch of times by now. And for this, let me first tell you what this algorithm actually does. It's a quantum algorithm that's meant to approximate the solution to classical constraint optimization problems. So these are problems where you have some objective function that you maximize over these n sort of bit values or plus or minus 1 values. And L local here means that you can write this objective function as a sum of terms with like some coefficient here, j, and a product of L of these values, zi. Now, if we have such a constraint optimization problem, we can naturally associate a commuting Hamiltonian with this, which is just the Hamiltonian that you get by replacing these bits z here by the corresponding Pauli matrices. And then the maximum eigenvalue of this Hamiltonian is exactly the same as the maximization here. Now, what QAOA does is it prepares a particular quantum state, which is this. How do you get this quantum state? So you start from the sort of equal superposition over everything, which is this plus state tensor n. And then you evolve by some sort of time, if you like, gamma 1 with this COP Hamiltonian Hn. And then you do an evolution independently on all of the qubits with the Pauli X matrix with some time beta 1, and so on. You just keep repeating this for some number p of layers. So I'm not going to give much intuition for why this should work, but the hope is that you can find good values of beta and gamma such that if you measure this output state here in the computational basis, you get a good solution to this constrained optimization problem after converting, say, from bits to these ±1 values. And in fact, if the number of layers here, p goes to infinity, you can prove that you can find choices of beta and gamma such that you get the optimal solution to the COP. So really the question here is what happens for like small p, right? Because this is meant to be some kind of near-term algorithm where we implement some really like limited number of layers of these evolutions. So there are two problems here. One is how to find good choices of beta and gamma, and the other is once you found these choices, how good is your solution? We ignore the first problem. We just assume that you've like magically found optimal betas and gammas, even though this may be hard in general. And we prove that even then there are strong limitations on the performance of this QAOA at level p, which is little o of log n. So it's like slightly super constant. But importantly, this works also for constrained optimization problems that have dense constraint graphs, so that have sort of very many terms here, and any set of L bits here can be involved in any terms. Let me briefly mention some previous results here. So the setting that's mostly been analyzed so far is the case of sparse constraint graphs, because then you can again do some kind of correlation tracking similar to the shallow circuits thing that I described earlier. And in that case, there are many limitations known from these papers. In the case of dense COPs, there's this very recent paper, which is really nice and that we took a lot of inspiration from as well, which proves that in the asymptotic limit of infinitely many bits, the expectation value of measuring the state and then plugging the solution into the constrained optimization problem, there are limitations on how well this expectation value can perform for a constant number of layers. So our results improve upon this in two ways. Firstly, instead of having a constant number of layers, we have this slightly super constant number of layers. And then secondly, instead of looking at the expectation value, we actually prove that the probability of getting a good solution is really quite small. Okay, how do we prove this? We prove this using a structural property of COPs called the overlap gap property. And formally, a COP has this overlap gap property if any kind of good solutions are either close or far. And in particular, if the parameters here are sufficiently strong, then you get clustering of good solutions. So all of these blue dots here are kind of the good solutions that are close enough to optimal. And the OGP says that with sufficiently strong parameters, at least, all of these good solutions are grouped in these clusters, which are linearly far away from each other in the Hamming cube. And this paper here shows that, in fact, for random spin models, which is the case that we're mostly interested in, this OGP holds, even though I should point out that they don't get the sufficiently strong parameters here to get this clustering, but it seems to be implicit in their proof that this holds as well, but technically it still needs to be verified. Okay, so let's say we have a COP that has this sufficiently strong OGP that we get the clustering. How can we use this to prove limitations on QAOA? Well, we need one additional property, which is symmetry. So we only look at COPs here, which are symmetric under flipping all signs. So for example, if you have an L local COP, this would be the case if L is even. So let's say this has the strong OGP so that we get clustering and we run QAOA with level P being little o of log n. And now we want to do the argument that I had on the very first slide of, you prove concentration, you prove that good solutions can't be concentrated, and you get a contradiction. How do we do this here? We prove that because QAOA is an instance of this dense Hamiltonian evolution, and also these extra technical conditions turn out to be satisfied, the QAOA output state is k epsilon local for k being little o of n and the sub-exponential epsilon that I just copied from the concentration bounds that we got in general. And now suppose for contradiction that the QAOA measurement distribution produces a good string, where good is in the sense of this overlap gap property, with probability at least root epsilon. So this is really like not a very strong hope, right? We only hope that we get a good solution with this sub-exponential probability here. But nonetheless, this turns out to not even hold. So if you make this assumption that what you can show is that by the concentration properties of approximately local states, almost all of that root epsilon probability weight must be concentrated on a single cluster. Intuitively, this is because all of the other clusters are kind of too far away, and they're too far in the tail of the distribution for there to be hardly any weight on them. Okay, so this is the concentration part of the argument. Now we need the other part that says that good solutions can't be concentrated. And for this, we use the symmetry. So because the COP is symmetric under flipping signs, it's fairly easy to show that the QAOA output state must be invariant under flipping all of the bits, so applying Pauli X to all of the qubits individually. This is already observed in this earlier paper by Bravi et al. And this means that each cluster in the output distribution of the QAOA state must have a kind of partner cluster, right? Cluster in the OGP sense, where all the bits are simply flipped, but the weight of these partner clusters must be equal by symmetry of the QAOA state. But this is a contradiction to 3, because in 3 we prove that all of the weight must be concentrated on just a single cluster, so there can't be a sort of far away partner cluster with equal weight as well. So the conclusion is that for such COPs, QAOA with level p being little o of log n cannot produce good solutions with probability higher than the sub-exponential here. Okay, let me wrap up. We proved concentration bounds for the outputs of shallow quantum circuits, also ejective matrix product states, which I didn't talk about at all, and the outputs of dense Hamiltonian evolution. And the main proof technique is always to approximate these states by low-degree polynomials of local operators, which gets you these local approximations. And by combining these concentration bounds with this overlap gap property, we get strong limitations on the QAOA for symmetric dense constraint optimization problems at this slightly super constant level as well. So there are many open questions here, but let me just mention the 2 that I find most interesting. Firstly, for dense Hamiltonian evolution, we don't get the same kind of Chernoff style decay that we get for shallow quantum circuits when we get sub-exponential decay. So it's very natural to ask what the best decay is that you could hope for in the case of dense Hamiltonian evolution, and in particular, whether you can get Gaussian concentration for that case as well. And secondly, on the QAOA side, currently the proof really relies on the symmetry requirement here. So if we have non-symmetric QAOA, do we still get some kind of limitations using these concentration techniques? Okay, so I'll stop here and thank you for your attention.